Have you ever looked up at the night sky and wondered, how far away are those stars? How vast is the universe that stretches out before us, seemingly infinite and full of mysteries? These questions have fascinated humanity for millennia. Ancient astronomers pondered this question for centuries. They were the first to systematically observe the heavens, recording the movements of celestial bodies with the naked eye and rudimentary instruments. They saw the stars as points of light fixed on a celestial sphere. To them, the night sky was a vast, unchanging canvas, with stars forming familiar patterns and constellations that guided their way. Imagine this sphere as a giant, invisible dome surrounding the Earth. This concept of a celestial sphere was central to their understanding of the cosmos. The stars seemed unchanging, but their true nature remained a mystery. They were distant suns, but this was a fact unknown to the ancient astronomers. One of the earliest attempts to measure cosmic distances came from the ancient Greeks. They were pioneers in the field of astronomy, laying the groundwork for future discoveries. Hipparchus, a brilliant astronomer, developed a method called parallax. This was a groundbreaking technique that allowed him to estimate the distances to the stars. Imagine holding your finger in front of your face and closing one eye, then the other. Your finger seems to jump back and forth. That's parallax. This simple demonstration shows how our perspective changes with position. Hipparchus realized that nearby stars should also show parallax as the Earth moved around the Sun. By carefully measuring these tiny shifts in a star's apparent position, he could calculate its distance. This was a monumental achievement for the time, considering the limited technology available. Unfortunately, the technology of his time limited his accuracy. The instruments were not precise enough to detect the small shifts in position that parallax required. Despite these limitations, Hipparchus's work laid the foundation for future generations of astronomers. His methods and observations were recorded and passed down through the ages, inspiring countless others to look up at the stars and wonder. The quest to measure the cosmos had begun. From the ancient Greeks to modern astronomers, the journey to understand the universe continues, driven by the same sense of wonder and curiosity that inspired Hipparchus and his contemporaries. Centuries passed, and the invention of the telescope revolutionized astronomy. Galileo Galilei, a pioneer of the Renaissance, turned this new instrument to the heavens. He observed the phases of Venus, proving that it orbited the Sun, not the Earth. This discovery dealt a blow to the ancient geocentric model of the universe. Another key figure was Giovanni Cassini. In the late 1600s, he used parallax to measure the distance to Mars. Cassini's observations helped to refine our understanding of the solar system's scale. With telescopes, astronomers could now see farther and clearer than ever before. The 19th century witnessed a major breakthrough in measuring stellar distances. Friedrich Bessel, a German astronomer, successfully used parallax to determine the distance to a star called 61 Cygni. This was a watershed moment. Bessel's measurement provided the first direct evidence that stars were indeed suns located incredibly far away. It confirmed what astronomers had long suspected: the universe was vast beyond imagination. In the early 20th century, Henrietta Swan Leavitt, an American astronomer, made a remarkable discovery. Working at the Harvard College Observatory, Leavitt was part of a team known as the Harvard Computers, a group of women who made significant contributions to astronomy. Despite the limited recognition they received at the time, their work laid the foundation for many astronomical breakthroughs. While studying stars in the Magellanic Clouds, she noticed a special type of star called a Cepheid variable. These stars are unique because their brightness changes over regular intervals, a phenomenon that caught Leavitt's keen eye. She meticulously recorded the periods of these pulsations, which ranged from a few days to several weeks. These stars pulsate, growing brighter and dimmer over time. Leavitt's detailed observations revealed a pattern. The longer the period of pulsation, the brighter the star. This was a groundbreaking insight because it suggested a direct relationship between the period of a Cepheid variable and its intrinsic luminosity. Leavitt found a relationship between a Cepheid's pulsation period and its intrinsic brightness. This relationship, now known as Leavitt's law, allowed astronomers to determine the actual brightness of a Cepheid variable by simply measuring its pulsation period. By comparing this intrinsic brightness to the star's apparent brightness as seen from Earth, they could calculate its distance. This discovery provided astronomers with a powerful new tool, a standard candle to measure cosmic distances. Standard candles are objects with known luminosity, and Cepheid variables became one of the most reliable standard candles in astronomy. This breakthrough enabled astronomers to measure distances far beyond our own galaxy, opening up new frontiers in the study of the universe. Enter Edwin Hubble, who used Leavitt's Cepheid variables to make a groundbreaking discovery. Hubble, working at the Mount Wilson Observatory, identified Cepheid variables in the Andromeda galaxy. By applying Leavitt's law, he calculated that Andromeda was far outside the Milky Way, proving that our galaxy was just one of many in the universe. He observed that galaxies were moving away from us, and the farther away a galaxy was, the faster it was receding. This observation led to the formulation of Hubble's law, which states that the velocity at which a galaxy recedes is directly proportional to its distance from us. This was a monumental shift in our understanding of the cosmos. This led to the theory of an expanding universe, a cornerstone of modern cosmology. The idea that the universe is expanding has profound implications for our understanding of its origin, evolution, and ultimate fate. Leavitt's and Hubble's contributions have thus become fundamental to the field of astronomy, shaping our comprehension of the vast, dynamic universe we inhabit. Section 5. Modern Methods, a Cosmic Distance Ladder. Today, astronomers use a variety of methods to measure cosmic distances. Imagine these methods as rungs on a ladder, each one reaching farther into the cosmos. For nearby stars, parallax remains a reliable technique. The European Space Agency's Gaia mission, launched in 2013, has taken parallax measurements to a whole new level, mapping over 1 billion stars in our galaxy with unprecedented accuracy. Section 6. Gaia, mapping the Milky Way and beyond. Gaia is like a cosmic surveyor, meticulously charting the positions and motions of stars in the Milky Way. Its data has revolutionized our understanding of our galaxy's structure, history, and evolution. Gaia's measurements also help us refine the cosmic distance ladder, improving the accuracy of our distance estimates to more distant objects. Section 7. Redshift and the far reaches of space. For galaxies far, far away, astronomers rely on redshift. Remember Hubble's discovery? Light from receding galaxies gets stretched, shifting towards the red end of the spectrum. The greater the redshift, the farther the galaxy. Redshift measurements have allowed us to probe the depths of the observable universe, revealing galaxies billions of light-years away. Section 8. Radar, lasers, and the gravitational lens. To measure distances within our solar system, astronomers use radar and laser ranging. By timing how long it takes for a signal to bounce back from an object, we can determine its distance with high precision. For extremely distant objects, like quasars, astronomers can sometimes exploit a phenomenon called gravitational lensing. This occurs when the gravity of a massive object, like a galaxy cluster, bends and magnifies the light from a more distant object behind it. Section 9. Unveiling the universe, past, present, and future. From the ancient Greeks gazing at the stars, trying to make sense of the patterns they saw in the night sky, to modern astronomers using sophisticated instruments like telescopes and satellites, our quest to measure cosmic distances and understand the universe has been a long and rewarding journey. Over centuries, we have developed new methods and technologies to peer deeper into space. Each new discovery builds upon the work of those who came before, creating a rich tapestry of knowledge. The ancient texts and early telescopes laid the groundwork for the advanced tools we use today. Pushing the boundaries of our knowledge, these advancements reveal the awe-inspiring scale and grandeur of the universe. We now know that our galaxy is just one of billions, each filled with countless stars and planets. As technology continues to advance, we develop even more powerful tools to explore the cosmos. Futuristic telescopes and space probes are being designed to capture more detailed images and data than ever before. We can look forward to even more precise and revealing measurements, allowing us to unlock the secrets of the cosmos. These advancements will help us understand phenomena like black holes, dark matter, and the origins of the universe. Unlocking the secrets of the cosmos not only satisfies our curiosity, but also inspires future generations. The beauty and mystery of nebulae, distant galaxies, and cosmic phenomena captivate the imagination. Inspiring future generations to explore the vast expanse of space, we ensure that the quest for knowledge continues. Young astronomers and space enthusiasts will carry forward the legacy of discovery, pushing the boundaries of what we know and venturing into the unknown.